Good morning, everyone, and good afternoon, wherever you are. And first of all, I would like to thank you for your time, taking your time to listen to our webinar here. And I'm going to present you some very specific and very simple stages or steps on how to prepare a catalyst, characterize it, and make a catalytic test. And taking for it as an example the nickel-supported catalyst for the Sabatier reaction or the reduction of CO2 and the effect of the support on the catalyst on the activity of the catalyst itself. So the first thing is that we have to select the support. This is the first step. This is the most important step, I would say. Before doing anything, just conceive the process we're going to do in catalysis, and then select the support of your catalyst. The support of your catalyst is I would say, the most important things to be sure that you are collecting or selecting the correct support for your preparation of your catalyst, because your support is like an alumina or silica alumina, has to have a very special texture, and that is the surface area, porosity, and total pore volume. Why is that? Because the monolayer from the surface area is going to give us information about the amount of active metals we can support. The porosity of the pore size is another very important characteristic of the support that is going to control the diffusion of the reactant molecule into the surface area. Well, before I go forward, as a surface area, we have to make sure that we understand that we have two types of surface area on the support. The external surface area, which is outside of the pores, and this is make a small contribution to the total surface area of the support, as this may be 1 or 5, 10 meters squared per gram. While the surface area inside the pores is going to make a large contribution to the total surface area, and this could be 100, 300, 500 square meter per gram. So this is very important to understand that is when we prepare the catalyst, we would like to have all these active species to go inside the pore and be dispersed inside the internal surface area of the pores. This is where the dispersions take place of the active species. So the pore size also is very important. So we always speak about effective pore size. Okay, the effective pore size is going to control the diffusion of the molecules. Okay, and we're supposed to have the pore size should be about 4 or 5 times larger than the diameter of the reactant molecule, so it can diffuse very easily inside the pore to find the active species dispersed inside the internal pore, and also has to have a certain size, the pores, to let the product diffuse out from the pore to the external way. And the total pore volume, this is the volume which is taking at the maximum relative pressure on the adsorption isotherm, and this volume is taken into account when we prepare the catalyst, as we will see later. So the characterization of the catalyst, or texture characterization of the support, is done by the physical adsorption. Usually it is nitrogen at 77K, but could be argon or could be another inert molecule. That is to give us the adsorption and the desorption isotherm. So from the adsorption and the plateau, we can determine the surface area. And from the adsorption desorption, or from the adsorption desorption isotherm, we can determine the size of the pore. And the last point, at the highest relative pressure on the adsorption isotherm, we're going to get the total pore volume. The next step is the determination of the acidity of the support. It is important to know if your support has acid sites, because in many cases, the acid site also can act as active sites. So in order to measure the acidity of the support, we can use ammonia. If you like to determine the total acidity of your support, is ammonia, because ammonia is a base molecule and very small molecule, can diffuse into all kinds of pores, the small pores and large pores. But sometimes the small pores will not make too much contribution to the activity of the catalyst because they're very small. So in that case, we can change the probe molecule from the ammonia to isopropylamine. Isopropylamine is a branched molecule, is much larger than ammonia, and can diffuse only in mesopores of the support, and can determine the bronzed acid site. And well, in the case of ammonia, I would say that ammonia can be done very easy because it's a gas. Okay, but the isopropylamine is a liquid, so you have to have a system that can evaporate the isopropylamine to saturate the sample. And the last one is we use the methanol. The methanol is also the method to measure the acid sites, the basic site, and the redox site on the support. Later on, we're going to see all these techniques used with the examples, so it can be very clear how to determine the acidity of the support. So after we get the catalyst, the support is characterized, we can now prepare the catalyst. So in this case, we took 2 times the total pore volume of the support, where we made the solution of the salt. In this case, we used nickel nitrate hexahydrates. So, and we calculate the amount of the salt to have more or less 5% of nickel on our catalyst. So the catalyst we're going to say is this is have 5% nickel on different support. Okay, we used 2 different supports. One is very high surface area support, and the other one is a low surface area support. Because we wanted to see that is the effect of the surface area of the support on the activity of the catalyst. Then, well, with impregnation, it's just on dry. We use this as the solution. Of course, the support was activated first, which was degassed at a temperature 200 degrees C under vacuum. Then was cooled down under inert gas, so it will not reabsorb the water from the atmosphere. Then we put the solution over the support and we stir it for 4 hours. In this case, because we only have a solution for twice the total pore volume of the support, all the liquid went inside the pores. So once we let it dry overnight, and then we dry it going 2 degrees per minute up to 100 degrees C to drive out all the water from the solution. And this is stayed about 12 hours at 110 degrees C. And then we proceed with the calcination going 2 degrees per minute up to 500 degrees C. Also for 12 hours. This is the way how the catalyst was prepared. Then after we get the catalyst prepared, we proceed with the chemical characterization of the fresh catalyst. Okay, so before doing anything, it's just we need to characterize the fresh catalyst. So we did we used the technique temperature program reduction as is this very powerful techniques, and everybody in catalysis has to use it because it can give us a very important information about the catalyst, and the interaction between the active species and the support is very important. So that interaction can give us information about how the active species is going to disperse and how stabilized will be when the reaction conditions go to very high temperature and higher pressure. So this technique is very important and also is used to calculate the total amount of nickel oxide we have, because this is a quantitative analysis. If the TCD is calibrated with hydrogen, we can calculate the amount of hydrogen consumed by the catalyst, and this should correspond to the amount of nickel oxide we have on the catalyst, because the TPR is a bulk reduction. So everything will be reduced, not only the surface, but also the nickel oxide inside the bulk of the support. Once we reduce the sample, we proceed with titration of the active species available on the surface. So sometimes it's not very important to know if we have 5% or 10% of oxide. What is important for us to know how many of these active species remain on the surface, and that's called dispersion. And this are accessible on the surface for the reaction. So this is very important for us in catalysis to measure the amount of accessible active species on the catalyst. So we did it by using hydrogen as a probe molecule, because nickel, we know nickel is very, very active elements and can absorb hydrogen. So we used hydrogen as a probe molecule to titrate and calculate the amount of accessible nickel on the surface. Once we had the catalyst characterized, for the support and the catalyst. We proceed with the catalytic test with the nickel supported catalyst for the Sabatier reaction. The Sabatier reaction is a very well-known reaction. It's just to reduce CO2 with hydrogen and to produce better molecules like CH4 and other products. Sometimes we go to methanol and other alcohol. So the conditions where we used a combination of flow 1 to 4 CO2 to hydrogen, and we work at 50 bar of pressure. Okay, so we went up to 600 degrees C. So our conditions was 50 bars and up to 600 degrees C for the reaction. Now, determination of the possible cause of the activation of the catalyst is very, very important in catalysis to characterize the catalyst before the reaction and after the reaction, because we need to find out what are the causes of the deactivation of the catalyst. Okay, so that's the activation of the catalyst can be due to several things. Could be due to the deposition of carbon by cracking or as a product, and in this case for the Sabatier reaction, one of the products is graphite. So the graphite is going to be produced and is going to cover the active species on the surface. And once it's covered the active species, then the catalyst start deactivating because it's preventing the direct contact between the reactant molecule and the active species. Another phenomenon of deactivation is the sintering of the active species. Sintering means that it's the small and well-dispersed active particles are going to move and is going to form larger particles, as it's called sintering, and those reducing the active surface area where the reactions take place. So this is the two important parameters to be known as a cause for the deactivation of catalyst. There's another effect could be the sintering of the support. Sintering of the support means collapsing of the pores at high pressure and temperature, and if the catalyst surface collapse, then we have less specific surface area, and therefore also can cause of the active particle to center. So all these three parameters are studied very well and give us very good information about the deactivation of the catalyst. So once how we do the testing to find out what are the causes of the activation, the first thing is because the catalyst already had been tested, we have to clean the catalyst. We flow in inert gases through the catalyst bed at high temperature to remove any products from the reactant molecules and any product from the production of the CH4 or whatever we have on our catalyst. So we have to clean the catalyst first. The second thing is that we do, as in this case, we know that we have graphite that could be causing the deactivation, or could be, in other cases, we could have carbon as cracking of the hydrocarbon molecule. So we have to find out if really we have carbon on the catalyst. So we proceed with the techniques called temperature program oxidation. In this case, we flow 5% oxygen in helium over the catalyst, and we start heating up the temperature up to the 500-600 degrees C until we see the formation of CO or CO2 if we have carbon on the catalyst. So if we can see consumption of oxygen, is because we have carbon, and we could conclude that the carbon being deposited there or graphite is one of the causes of the deactivation of the catalyst. We know this is the graphite is a material which cannot be oxidized at low temperature, so we went to very high temperature, and also we suppose that the nickel catalyst is going to promote the oxidation of the graphite to CO and CO2. In this case, when we do that, of course, we use two techniques, as I'll show later. For the simple reaction or simple processes, as we use TCD, thermal conductivity detector, and when we have more than one product, we have to use the mass spectrometer. So as we will show you later, that we have both techniques, that we have the TCD and we have the mass spectrometer to detect all different products, as the TCD cannot identify the products coming from the reaction. So we have to use a mass spectrometer in that case. Then after the TPO, at this stage, the catalyst is being oxidized. So we reduce the catalyst again with hydrogen by doing TPR. So we recover the nickel, and we proceed with the titration of hydrogen to determine the dispersion. Okay, so that this is if the dispersion is going down, it's because the particles are being centered and we are losing active area. It is very important to understand the difference between the specific surface area and the active surface area. The specific surface area is the surface area of the support, measured by nitrogen at 77 K, while the active surface area is the area occupied by the active particles where the reactions take place. So in this case, we're talking about the active area. Then how do we know if it's we have sintering, we have the cause of the activation by sintering of the active species? We just compare the dispersion before the reaction and after the reaction. If the dispersion is going down, it means that we are sintering the active particles and we are losing active area. So this is another very easy way to find out if we have the sintering of the active species, that's causing the deactivation of the catalyst. So let's show you what we have done in this work. Is the first thing that we, as I said, we characterize the texture of the solid. In this case, we use a micrometric reflex. It's a high vacuum system, so we could use 3 samples at the same time. And from it, what we can collect is the amount of nitrogen being consumed as a function of the relative pressure. So as you can see, in this case, you can see that we have the adsorption isotherm, and we can show that we have 2 supports in this case. One of the supports called alumina trilobe, and it is about 310 meters squared per gram, while the lower one is alumina tablet, which is much less lower surface area, it's about 92 meters squared per gram. And of course, the pore volume is for the first one. The upper one, the alumina trilobe, has 0.67 cubic centimeter per gram, while the alumina pellets or tablets, it has 0.26 milliliter per gram. So from the adsorption isotherm, we can see that both solids have the type 4 adsorption isotherm, which correspond to mesoporous solids. The next step is we need to find out if the supports are acid. So we use the ammonia. The first thing is to measure the total acidity of the catalyst. As I said, ammonia is small probe molecules, can interpenetrate all the pores, and we can give us the total pore volume. Okay, so if we are interested to measure the total acidity of the support. If you are interested to measure the total acidity of the support, the ammonia is a good probe molecules. And it's very easy because it's almost a gas. So it can be done very easy, and we can use a TCD to determine the amount of ammonia being absorbed by pulsing ammonia or dissolving ammonia. So in this case, we like to find out the acid strength on the catalyst. So we used ammonia. So in order to do these methods for the ammonia, the first thing we have to degasify the preparation or to prepare the catalyst. Degasification and preparation of the solid. What we do it is under vacuum high temperature. So we have to have the solid clean from any moistures. Then we saturate the sample with ammonia at room temperature, over near room temperature. Once we get the sample being saturated with ammonia, we increase the temperature to 75 degrees C to eliminate all physisorbed ammonia. It's very important to go to 75 degrees C because ammonia is almost liquid at room conditions. It can condense on the surface of the support. So we have to eliminate all this physisorbed ammonia. Then we applied the temperature program desorption. So by raising the temperature up to certain temperature, 500-600 degrees C. But in this case, we repeat the steps several times. So we saturate the sample at near room temperature and we dissolve it at different ramping rate, 2, 4, 6, 8, 10, 15, and 20 degrees per minute. Why we do this, as we can see on the right side, the curves, the different curve at different ramping rate, is because this allows us the shift on the maximum. And if we apply the Kissinger equation, we can determine the adsorption or desorption of ammonia, which is related to the acid strength on our support. So it is very important. If our support has a very weak acidity, then it's not going to work as acid sites because the reaction temperature is high for 400 degrees C for the reaction, and therefore the weak acid sites are not going to work. So we need to have the high desorption of ammonia, the larger peak on the right side, and from there we can calculate the heat of adsorption. As you can see on the right side, on the blue, is the heat of desorption for the low desorption peaks, which are on the peaks which is on the left side, while in the red side, the red curve on the right side, give us the desorption at a very high for the strong acidity. Okay, as you can see, this is 162 kilojoule per mole, while the other one is 67 kilojoule per mole. So this will give us a very good evaluation of the acid side strength. By as I said, it's a very simple equation of Kissinger equation, and can give us good information about the strength of acid side on our support. If we're not interested about the total acidity, but only the bronzed acid side, we use the isopropylamine as a probe molecule. Also, this is the same as we did before with ammonia. We saturate the sample with isopropylamine, but as I said before, the isopropylamine is a liquid. So we have to have an instrument that can evaporate the isopropylamine to saturate the sample. So we evaporate the isopropylamine, we flow an inert gas, we saturate the inert gas with the vapor isopropylamine, and we take it to the sample, and we saturate the sample that way. Then we start decomposing the isopropylamine by increasing the temperature. And as we increase the temperature, the amine is going to react with the acid side, with the bronzed acid side, and it's going to give us several products: propylene, ammonia, and acid side. So in this case, the reactions decomposition is going to similar to the Hoffman elimination, as you can see on the right side of the curve. So how we can calculate the bronzed acid side? We have to calibrate our mass spectrometer. In this case, we have to use a mass spectrometer, as we do have several products. As I said before, the TCD is not capable to identify this product, but the mass spectrometer, it can give us information about the three products. But in our case, we are interested about the formation of the propylene. So we can very easily calibrate the mass spectrometer with the propylene by injecting known amount of propylene, and therefore we can quantify the amount of propylene. And 1 mole of propylene formed corresponds to 1 mole of the bronzed acid side on our catalyst. So it's a very easy task, but it's very nice. We can calculate the bronzed acid side on the mesoporous solid. Why is it mesoporous? Because the isopropylamine is a branched large molecule, is not going to go inside the small pores. And this is our interest in catalysis, is the pores where diffusion of the reactant can be very easy. So the molecule can diffuse very easily through the pores with a certain size. The last method is this is the product for the seen by the Hoffman elimination of the isopropylamine, seen by the mass spectrometer. So we have the peaks on the right, which correspond to the isopropylamine in the blue. The green is ammonia, and the red is the propylene C3. And this is the one important products we have. So we can calculate the amount of bronzed acid side by calculating the amount of propylene produced by the reaction. The last method we have used is the acidity by the methanol. Methanol is very nice probe molecule. It can give us, as you will see later, very good information about the different active sites on the catalyst. So the first thing, of course, in this case is if we have oxide, we have to reduce the catalyst. So MXOY plus hydrogen at high temperature to give us the metals, reduced metal, and the water. So our system has to eliminate the water from the stream, so before going to the mass spectrometer or to the TCD. So we saturate the sample with methanols, and we start decomposing it by increasing the pressure as we did before. So if we have acid side, the methanol is going to give us a dimethyl ether. So we follow the dimethyl ether by the mass spectrometer. If we see dimethyl ether formed, it's because we have acid side on the catalyst. Now, if we see only carbon dioxide or carbon monoxide, then we say this is a formation of basic size. So we have basic size on the catalyst. So by the formation of CO2CO, it corresponds to the amount of basic size on the catalyst. And if we get a formaldehyde, then we say that we have a redox size on our catalyst. So you can see this methanol is very, very advisable to be used to determine all these three active sites on our catalyst. After we finish with the characterization of acid sites, Now we follow with the chemical characterization of the catalyst. In this case, we use, as I said before, the first technique, and this is widely used in catalysis, is a TPR, or temperature program reduction of the catalyst. As you can see here, is we have the two catalysts as we prepare 5% of nickel over the alumina 3 lobe with a high surface area, and the 5% of nickel over the alumina tablet with a low surface area material. So let's see now the effect of the support on the stabilization of the active species of the nickel. As you can see on the left, we have the 5% nickel supported on the alumina 3 lobe, and we can see two peaks, 692 and 725 degrees C. It is very, very normal to see that nickel is being reduced at high temperature, which means that the nickel has very good interaction with the support. So being stabilized by the support, and therefore the reductions take place at higher temperature. While on the right side, the 5% nickel over the alumina tablets, we can see that the two peaks also, but at much lower temperature. So the first peak is about 385 degrees C, and the second one is 492 degrees C. So the conclusion of these two peaks is the first one on the 3 lobes, high surface area, stabilize and interact very strongly with the nickel, while on the right side is the interaction very weak. So the 5% or the nickel on the alumina 3 lobe low surface area, it looks like that the profile of the reductions looks like pure nickel oxide. So here we have, on the right side is a 5% nickel oxide catalyst, while on the left side is a pure nickel oxide. So you can compare both of them, and you can see very similar profiles. So what that means to us is that the nickel pellets nickel low surface area does not interact strongly with the nickel. So we can conclude that this catalyst low surface area is going to sinter much faster. Why? Because when we start heating the sample, the reactor at high temperature and high pressure, the nickel may sinterize much faster in this case than the one in the high surface area support. This is one of our objectives, to see how the surface area of the support is going to stabilize the catalyst by itself. So in this case, this is after we finished with the TPR, as we have seen that we went to very high temperature, we thought that the nickel could be sintered. So we did not use that sample to do the catalytic test. So what we did here, we took a fresh sample again, the 5% nickel alumina 3 lobe and the 5% nickel alumina pellets, and we reduced it at higher pressure of hydrogen. It is very well known that if we raise the hydrogen high pressure, the reductions peaks are going to be a much lower temperature. And this is very advantageous for us, because if we can reduce the sample at lower temperature, we are minimizing the sintering of the active species. So as you can see on the right side is the same catalyst. It's a 5% nickel alumina 3 lobe, and you can see the peaks from 692, 725, it will be reduced to 385 and 478 degrees C. So at much lower temperature, about 300 degrees C below. And this is give us a good information about that. Is reducing the sample at high pressure, reduce the reduction temperature, and therefore minimize the sintering of the nickel. It is very important to reduce the sample in catalysis at high pressure to minimize the sintering of the active species. After the sample being reduced, we proceed with a titration with hydrogen to determine the amount of nickel surface accessible for the reaction. As I said before, I'm not interested about to know exactly how much nickel we have on the catalyst, but how many of those nickel they are on the surface of the catalyst accessible for the reaction. So the pulse chemisorption techniques is very well used technique to determine the dispersion. So how we do that? The condition is that we have 10% hydrogen argon, which is the active gas, and the carrier gas is pure argon. So we fill a loop. We know the volume of the certain loop at a certain temperature. We filled it with 10% hydrogen, and we pulse it over the sample, and we determine the amount of gas being adsorbed. So the profiles, as you can see here, is on the left on the side, that the first peak on the left comes very small. What that means, the large amount of hydrogen being adsorbed by the sample. And we keep going until we can see peaks equal in area. So this means that we have saturated the sample. So if we back calculate the amount of hydrogen being chemisorded by the high surface area material, which is 5% nickel aluminum trilobe, we can determine that we have 37% of dispersion. This is the left side. While for the other catalyst, which are low surface area materials, we did the same thing. As you can see, the first peak on the left side and on the right side, so the right side is much larger than the left side. If the peak is larger, it's because the sample is absorbing less. But we can see here is we see what has not been absorbed by the sample. Okay, so it's very easy to see that is the lower surface area material has much less dispersion. Is about 17% dispersion. So we can estimate now before doing any catalytic test that the first one of the high surface area material, because having a higher dispersion, is going to be much more active than the second one. Okay, after we do this analysis, we proceed with the reactions. Okay, the reaction is, as I said, we took both catalysts at 0.5 gram approximately. And we have went up from ambient temperature to 600 degrees C, ramping 2 degrees C per minute. So our methods to measuring the activity of the catalyst is really special, because what we did here, having the catalyst loaded inside the reactor at room temperature, we flow 1 to 4 CO2 to hydrogen at room temperature. So we stabilize the baseline, or the intensities, by the mass spectrometer, as you can see on the left side. Okay, we have the CO2, we have the hydrogen, and then we start heating up the reactor at very low ramping rate, 2 degrees per minute, because in this case we can see step by step how the reaction proceeds. Okay, if you can look on the left side, you can see the green line, which is the production of CO. So the high surface area catalyst produce CO first at 250 degrees C. And then we can proceed with heating the reactor at 325 degrees C. Then the CH4 start forming. So you can see the pink colors is the CH4 going up. And we proceed with the reaction about 24 hours. So on the same figures on the left, it has a 24 hours time, until we can see that the CH4 signal, the partial pressure in the mass spectrometer, starts going down, and the partial pressure of CO2 starts going up, the hydrogen CO. So what that means is the catalyst is being deactivated. So once we get to a point, we stop the reaction, and we proceeded to find out what are the causes for that deactivation. But before we proceed that, as you can see on the right side, for the low surface area materials, we went about 20 hours, and you can see that the CO is not present. So CO has very small signal, so it did not form CO, that low surface area materials. So the partial pressure of CO is very low. While at 325, we can see that the CH4 start forming. Okay, it's more or less 325 for the high surface area and 325 for the low surface area materials, catalyst. Both of them produce CH4. But the difference in the low surface area materials, it deactivates much faster. It did not work more than 15 hours. So it start deactivating very fast. In this particular case for Sabatier reaction, we can suspect that the deactivation is due to the deposition of graphite. As you can see on the upper side, the right side of the screen, all the products of the reaction, Sabatier reaction, and one of the products, the first one, is graphite. So we can suspect that the graphite is being deposited on the active species and preventing the interaction between the reactant molecule and the active surface area. But we'll see later on how we can see that. So now we can proceed with after the activation and how to find out what are causing the activation of the catalyst. So as I said before, the first one is the deposition of graphite. And the second one could be the centering of the active species, as I said before, also the centering of or collapsing the surface area. So what I did in this case is that we start to eliminate the graphite or the carbon by doing a TPO, flowing a 5% oxygen and helium with 100 ml per minute and ramping 10 degrees per minute up to 900 degrees C. Okay, we know very well that the graphite is going to be oxidized at much higher temperature, but we suspect that the nickel alumina catalyst is promoting the oxidation of graphite. How do we know that? Is as you can see that the detection of CO and CO2 by the mass spectrometer. On the right side on the curve, you can see the A is the consumption of oxygen by the low surface area material, catalyst. B is the consumption of oxygen by the high surface area materials. Both cases they produce CO2, but very little signal of CO. Means that also the nickel supported catalyst is going to promote the oxidation of CO to CO2. So we don't see much CO, but CO2. But also we can observe that the amount of oxygen for the high surface area material is much higher producing CO2 than the low surface area material. Again, it is all our results agreed from the beginning that the high surface area material is going to have more activity of producing CH4, but also as it produces CH4, it's going to produce graphite and is going to activate the catalyst. And therefore, we can quantify the amount of graphite of the carbon by calibrating the mass spectrometer with CO2 or oxygen, and we can calculate the amount of CO2 if we wish to do so. Now, after we oxidize the sample, the TPO, we proceed with the reduction of the catalyst. Okay, because the catalyst now is oxidized, and we need to reduce it in order to follow with the following techniques. So in this case, we reduce the sample with the TPR, which has been previously oxidized, and we can see a profile very similar to a pure nickel oxide. Okay, we get 286 first peak and 405 degrees C in the second peak. So in this case, we know that the catalyst has been completely reduced because we follow the baseline of the TCD. So when the baseline comes back to 0, we can calculate even the amount of nickel present on the catalyst. We know that for 1 gram of pure nickel oxide can consume about 300 milliliters per gram of hydrogen. So in this case, we calculate 265 ml per gram. It's not that bad, but it could be due to the lower numbers because it could be due to the maybe bad calibration of the TCD at high pressure. But this is giving us very similar, very good result, a very close result to the pure nickel oxide. So we can conclude from that all the nickel has been, which has been oxidized, now has been reduced. So now the sample is being reduced. Why we do that is because we are going to follow with that dispersion as we did before. And for that, the nickel has to be in the nickel oxide, nickel metals, not oxide, because the oxide will not absorb the hydrogen. This is what we have to reduce the sample before doing the post-chem sorption. So in this case, we repeated the post-chem sorption with hydrogen at 35 as we did before. So the left side is a nickel on 3 lobes, the high surface area materials, and on the right side is the low surface area material. As you can see in both cases, the dispersion went from 37 to 23 for the high surface area materials, and for the other one from 17 to 5. You can very easy, you can look for the first peak on the left side and the right side, and very much larger than the one before the test. So this means that it's the active species are being centered. And if active species are being centered means that's also causing the deactivation of the catalyst. So we can conclude in this case that we have 2 causes of the deactivation. One is a deposition of graphite on the active species, on the surface of the active species. And the second one is centering of the active species by growing the active particle and therefore absorbing less hydrogen, as we see here. And by centering, we are reducing the active surface area and less active area for the reaction. And therefore, also as a deactivation of the catalyst. So we can see how we can characterize the catalyst before the reaction and after the reaction, because not only is important to know and to characterize the fresh catalyst, we need to find out what are the causing of the deactivation of the catalyst. So these 2 techniques are very easy to use and can give us very good information about the causing of the activation of the catalyst. We could also, but we have not done it here, we can also measure the surface area by BT. But in this case, we use a very special technique, as I'll show you later, which is a technique called ICCS, and is an in situ catalyst characterization system, which is connected to the reactor and allows us to characterize the catalyst before and after reaction in situ. So we don't have to remove the catalyst from the reactor. This is very important because it avoids you to handle the sample or lose some weight or something like that, or can expose the sample to the atmosphere with water. So the ICCS allows you to do all these techniques to be used in line and in situ without having to remove the catalyst from the thermal catalyst bed. So we did not measure the BET surface area because we had to remove the sample. The ICCS does not allow to measure the BET surface area because it needs nitrogen, liquid nitrogen, and this is the way but we know that the catalyst has been deactivated because of sintering and because of the graphite being deposited on the carbon. This is more or less a picture of our lab here. And as you can see on the left side, we have the ICCS, the small units, and the FR, micro reactor, FR100. And on the left side is a picture of the laboratory. As you can see, number one is a system which is called the in situ catalyst characterization, is ICCS. As you can see, it's connected directly to the reactor. And the advantage of this instrument is that it can be connected to any external reactor. Could be industrial reactor or homemade reactor. You can move it, very small unit. You can move it to one place to another, and just you connect it to the inlet of the reactor and the outlet of the reactor. So it has everything. It has a TCD to measure, to detect the incoming gas from the reactor. It has a built-in trap to trap the water. Remember, when you do TPR, you have water as a product of the reaction, and it has to be trapped before getting into the TCD. And that trap does not require to prepare any cryogenic dewar or any cryogenic system, because it works with a Peltier system. Is once you turn on the instrument, it goes directly to 4 degrees C. Okay, so you can also come up between 4 and 60 degrees C. You can change the temperature, so that at 4 degrees C the water will be trapped before reaching to the TCD. So it will not alter our TCD profile. Number 3 is we have a micro GC, so we can also follow all the products, not only the CH4, but we can follow, maybe you have methanol and other products. We can also, it's connected directly at the exhaust of the reactor. Number 2 is a FR reactor. This is micro-mix FR reactor, could be FR100, which is 1 reactor, or FR200, called 2 reactors simultaneously. So can work in parallel or could be connected in series. And also we can work up to 100 bar or 200 bar. The number 4 down below the ICCS is a mass spectrometer. We use the MKS Series 2. Is also connected to the exhaust of the reactor to follow online our products. This is how we followed online the product for the reaction, and how also we follow the products for when we did isopropylamine or methanol. So we use it online to detect all the products coming from the reactor. This is our 2930 AutoChem. We use this to determine the isopropylamine and methanol. Okay, as you can see on the left side of the instrument, they have the vapor generator where we place the isopropylamine, and we can heat it up and control very precisely the vapor pressure of isopropylamine that can be dosed to the sample. So we can calculate the total amount of isopropylamine that's used to saturate the sample. And after that, we can do the TPD or desorption for isopropylamine to measure the amount of propylene formed, and therefore we can quantify the bronzite acid site in our catalyst. So this system is 2930, can do all what you can see on the left, the post-chemical absorption, TPR, BET, possible breakthrough analysis, metal dispersion, etc. So it can characterize very wide characterization of the catalyst in any possible way. Conclusion of the work, the first thing is that we conclude that nickel-supported catalysts are active for the reduction of CO2, therefore reduction for good active catalyst for the Sabatier reaction. The high surface area support, as we have seen, is essential to produce highly active catalysts. We could see that the high surface area has much higher activity for the CO2 than the lower surface area material. Determining the texture of the support is highly recommended. It is because the effective pore size and the effective surface area, specific surface area, are essential for the activity of the catalyst. Because the surface area from the monolayer, we could calculate how much metal we could load on the surface of the catalyst, and the pore size, we call it the effective pore size, can allow the diffusion of the reactant molecule without any problem into the pores to find the active species dispersed inside the internal surface area. The temperature program reduction is highly used also in catalysis. It evaluates the role of support to disperse and stabilize the active species, but also can quantify the amount of oxide in your sample, because the temperature program reduction can reduce all the oxide in your sample. Okay, so in this case, we have nickel oxide. We can reduce the nickel oxide on the surface as well as the one in the bulk. So we can calculate the total amount of nickel oxide we have on the catalyst. It's a quantitative analysis. The pulse chemisorption techniques quantify the amount of active metals on the surface. Okay, so it is used to determine the dispersion of the active species, and also by comparing the dispersion between before the reaction and after reaction, as we have seen before, we can illustrate very easily the cause of the deactivation of the catalyst by sintering of the active species. Temperature program oxidation permits the evaluation of the amount of carbon. Okay, as we have seen, it's forming the products as a CO or CO2. So we can tell if we have cracking, for example, if we have hydrocarbon molecule as cracking, therefore the carbon is deactivating the catalyst. In this case, we have graphite. Also, we could evaluate the amount of graphite we have by raising the temperature at about 900 degrees C. And we suspect that the nickel oxide was a good oxidation catalyst to promote the formation of CO2 from CO. The use of the techniques are a very high importance due to their easy access, so everybody can have it, because some of the techniques are other techniques, for example, spectroscopic techniques using ESCA or XPS, whatever you like. It's much more, I would say, it's not that easy to access them, because it's much more expensive system. Okay, while these techniques, the temperature program reduction, oxidation, are very simple techniques, can be very easily accessed to any researcher, any research center, or any university, because of their prices much less than any sophisticated technique for their characterization. The in situ catalyst characterization, I insist on this, is a very small technique. It's a new instrument in the micromathematics, and it's unique and very important because it can be connected to any industrial or any homemade reactor, especially for the university, for example, where you have several reactors, several students. Each one of the students has different reactor, homemade reactor, and they have different reactions. So they can use the ICC system, can be moved from one reactor to another reactor. It just has to be connected to the inlet and the outlet of the reactor. So what we need in this case, only a reactor with a controlled oven. So you can control the temperature of the oven, you can ramp it, and the rest of the analysis can be done directly, automatically by the ICCS. It's an automatic system. You program it to do TPR and TPO automatically, so it will do everything is to be required to characterize the catalyst. The Micromix FR100 or 200, as I said, 100 because I have one reactor, 200 can have two reactors, so can be connected in series. They are very versatile system, is automatically operated up to 100 bar. We have an option to go 200 bar, and especially they have the liquid gas separator. The system, the reactor is characterized by having the liquid gas separator, so it can be set at different temperature. Remember, this is, as we have seen before, that the Sabatier reaction produced too much water. So we have to trap the water, we have to eliminate the water under high pressure. So the system, the liquid gas separator or the FR100, can eliminate and remove the water from the stream when we set the liquid gas, the system at 4 degrees C. So it will condense the water and start taking the water or removing the water under pressure. So we don't have to move or to change the pressure. So you can see the water is dropping out during the reaction. The temperature program oxidation, TPO, permits the evaluation of the amount of carbon, as I said, if you have cracking or you have graphite, as in this case. So this technique is used Also, to regenerate the catalyst, once we remove the carbon or the graphite from the catalyst, we can the catalyst can be regenerated, and we can we can make the reaction again. So it's a regenerating the catalyst. If we do TPR, TPO cycling, we can tell how many cycles we can characterize the catalyst. And of course, we understand that every time you do TPO or TPR, you can center a little bit the active species. So your catalyst is going to be less active than the first time. So the activation starts going lower and lower every activity by repeating the TPO and TPR. But give you good information about how many cycles you can use your catalyst, and also is a technique to regenerate your catalyst. So the use of this technique is very highly important in catalysis. It's very easy and very access to many people and produce important results as was shown in this work. The micromolecular in situ catalyst system, as I said, is unique and can be connected to any. I insist on this because it is new for us, a new system in micromolecules, and can be a very good tool for any people who work on catalysis. Thank you very much, and hopefully we can use these slides to help people, especially the people who are starting with catalysis, to understand the steps by step how we prepare and characterize the catalyst, and we make the catalyst test.